The objective of this project is to actively balance an inverted pendulum by controlling the motion of an inverted pendulum's base. Before getting too deep into the details, let's start with a high-level understanding of the hardware and system we're working with.
3, go. Alright, so now we're going to go over our customizable cart that we have for our inverted pendulum. Now, as you see, we have a carbon fiber chassis. We wanted to go with something lightweight in order for our servo to be able to move around the cart itself without having to deal with too much weight from a more difficult, heavier body. So now we have our caster that acts as our pin joint. You see that we have our aluminum beam, which is our pendulum arm, which is glued onto the caster. This will allow for a very movable for our gyro. And then on the top, we're gonna have some US coins. We decided to go with the US coins for a mass because each one has a standard weight, and that way we know how much weight we're putting on to our pendulum arm. And that way it makes it a lot easier rather than using more mass that we don't have to worry about. On the bottom, we have our gyro that's attached already. We decided to go put the gyro on the bottom because it allows for more movement for our wires. That way we wouldn't have that much tension on our wires once the pendulum arm is moved before the chassis or after. And the wires will be connected to our Arduino and our breadboard, which will be located near the point of the pendulum on the base. That way we have more movement with our wires as well. And we have just a standard 9-volt battery, which acts as our power supply for the inverted pendulum. And it'll be located somewhat as such right here. And then on the bottom of our cart, we have 3 other casters. This will allow us to move. 2 of them are free, as you can see, and the other one is attached to our servo. Our servo is connected by 2 wooden blocks, and as you can see from here, that the servo is directly mounted to the caster, which is going to be the driving force for the cart in order to keep the mass balanced.
Let's take a second to go over the system block diagram for our inverted pendulum cart. For those of you who don't know, a system block diagram shows all of the elements of a system and gives you a sense of how they might work together. Our system for the inverted pendulum cart is comprised of 5 main components: a rotary actuator, a controller, a power supply, a sensor, and the inverted pendulum itself, which is comprised of a pendulum arm with a tip mass mounted on a movable base by a pin joint. Now let's talk about the architecture block diagram. An architecture block diagram shows all of the same components on the system block diagram, but with all of the various connections and interrelations between the components. The main component for the inverted pendulum cart is the cart body itself. Onto this, all of the other components are mounted. On this diagram, black lines show physical connections between components and red lines show electrical connections. The power source for all of the electrical components on this cart is a simple 9-volt battery. This battery will be mounted onto the cart using Velcro. Both the US Arduino and the hobby servo will be wired in parallel with the battery. Because the US Arduino takes 9 volts, while the hobby servo only takes 7.5, an 18 ohm resistor is wired in series with the hobby servo. The gyro, which measures the angular rate of the pendulum, is mounted directly to the pendulum arm. It is supplied power by the 3.3 volt line coming from the US Arduino. The pendulum arm itself is an aluminum beam. Coins are used for masses and glued onto this beam. The beam is mounted to the cart body on a caster wheel pin. The hobby servo is mounted underneath the cart body near the front in direct drive with the front wheel. All of the wheels and axles on the cart are simple caster wheels. There are 3 on the bottom and 1 used on top as the pin for the pendulum arm.
To be able to balance an inverted pendulum, there must be a way to sense the displacement of the pendulum for our cart to counteract against it. An L3 GD20 gyro sensor by Adafruit was used to provide feedback on the behavior of the pendulum. The gyro sensor is a microelectrical mechanical system, also known as MEMS, consisting of 3 micromachine tuning forks representing each rotating axis. The tines of the fork deflect due to Coriolis forces, which are detected by capacitive electrodes under the mass. Basically, the gyro sensor provides feedback on the angular rates of rotation in all 3 axes. This will be used to sense the rotation of the inverted pendulum about its pin joint, then communicate the data to a controller, which will process that data to cause the servo to react to return the pendulum to the desired initial condition, which, in our case, is the vertical orientation of a balanced inverted pendulum.
Servos are controlled by sending the servo a pulse width modulation signal, or a PWM. A PWM is a signal of repeating rectangular pulses of variable width or duration, which is measured in the milliseconds. Different pulse widths command the servo to go to different positions. What is the norm with servos is the pulse width of about 1.5 milliseconds is a command for the servo to go to its neutral position or center, which is the position where the amount of degrees the servo can rotate clockwise and counterclockwise is equal. For the most part, the minimum pulse width is about 1 millisecond and maximum pulse is 2 milliseconds for most servos. This is a total range from 1 to 2 milliseconds is about 180 degrees of the rotation of the servo arm. However, for most servos, non-feedback ones, even when you send a signal to the servo, you cannot receive a signal back to read the servo's position. You can either assume it is in the right position or measure the angle it is in by hand to verify that it's the position that you want it to go to. Inside the servo, there's a potentiometer that is used to get the servo motor to the correct position. You can attempt to modify the servo by tapping into the potentiometer inside and read it in terms of voltage, so you could get the position reading. Alternatively, you could include and wire up an encoder on the system to read back a position and speed with a timer.
A US Arduino was provided to serve as the controller for this project. Similar to the Arduino, it is an open source computing platform that utilizes the same coding infrastructure as the Arduino. This is useful as any coding needed can be derived straight from the Arduino website. The safe range for Vin is 7 to 12 volts. Any less will make the Arduino board unstable, and any more, and the voltage regulator may overheat and damage the board. Because of this, a 9-volt battery will be utilized to power the board in the absence of a laptop power source. In order to process data into the Arduino from the gyro, a program specifically made for the L3GD20 gyro sensor was derived from the Adafruit website to constantly track data from all 3 axes and list those values in the serial monitor of the Arduino program. The servo is controlled by adapting the sweep code found in the Arduino library to react only to the readings from the gyro instead of a continuous sweep. Since the pin joint is only rotating about one axis, the servo will only be programmed to react to the rotation in one axis. In this case, the servo will react when the x rotation exceeds the proposed boundaries. If x is greater than 5, the servo will rotate opposite of the rotation of the gyro, and if x is less than -15, the servo will again rotate opposite the rotation of the gyro. The opposite rotations will counteract the swinging pendulum to balance it back to its vertical position. The program was successful in actuating the servo in response to the rotating gyro, but in order to successfully balance the inverted pendulum, further analysis and calculations are required. Our approach consists of an analysis of a dynamic model of our inverted pendulum configuration. Using the dynamic model, we aim to generate a relation between servo sweep angle, gyro angular rate, and pendulum position.
Now we'll discuss the dynamics for the inverted pendulum system. So before we go into deriving the equations of motion for the inverted pendulum, I want to give you a background of what an inverted pendulum system is. So an inverted pendulum has a stiff bar of length L, which one end is supported by a pin joint on a cart, while the other end has a select amount of mass on it. So here we've illustrated a typical inverted pendulum system. As you can see, we have some of the forces acting on the inverted pendulum, with gravitational force acting on the pendulum bar itself, and two forces acting on the cart. One of the forces, Fv, is the applied force, which gives it the cart's motion, while the F sub F is the frictional force from the ground acting onto the cart itself. The centroid, or the center of gravity of the pendulum, is given by the following equations. As you can see, they are in the x and y coordinate. For the x coordinate, the L is the distance along the pendulum to the center of gravity, and the x is the x coordinate of the cart's position. On the bottom, we have illustrated free body diagrams of the three systems. So as you can see, in the first one, we have the cart and all the forces that act upon the cart. In the second one, we have the pendulum itself and all the forces acting on it. And in the third one, you see the distances to the forces that act upon the pendulum. So to develop our equations of motion for the system, first we have to determine the horizontal force that acts upon the cart. So to do so, we use the Newton's second law of motion, which states that the summation of forces is equal to the mass times acceleration of the system. So we've developed our equation, which shows the summation of all the forces that act upon on the system. As you can see, we have the force that is applied minus the force due to the horizontal motion of the pendulum, as well as subtracting the force due to friction of the ground. So we substituted the known forces into the equation to determine what the total horizontal force is. As you can see, the force due to friction is equal to some coefficient times the acceleration, as well as you can see that the force due to the horizontal motion of the pendulum is equal to the mass of the pendulum times the second derivative of the x component of the centroid of the pendulum. So while doing the second derivative of the centroid, and plugging it in, we get the following equation at the bottom, which is the total horizontal force of the cart. Now we must determine the vertical force acting on the pendulum. So the vertical motion of the pendulum can be represented by the following equation. We have the reaction force in the y direction on the pendulum minus the gravitational force, which is equal to the mass of the pendulum times the second derivative of the y component of the centroid of the pendulum. Now similar to the horizontal force, we take the second derivative of this time of the y component of the centroid, and by plugging it into the equation, we solve for the reactionary force Fy, and we get the following equation that's located at the bottom. Now we must determine the angular position of our system. So the relationship between the moment applied on an object and its angular acceleration is given by the following relationship, where m is the moment due to a given force and is defined as the cross product between the force vector and the position vector of the object with respect to the point about which the moments are being summed. I in this equation is the angular momentum of the object. For the pendulum, the summing moment around its center of gravity gives us the following equation, and by substituting the forces that we found in the previous sections, the horizontal and vertical forces, we obtain the equation as seen on the bottom. By simplifying the previous equation for angular position, we obtain the equation that is seen, and determining the final equation for angular position is given on the bottom. Now that we've determined the equation for the forces acting on the system as well as the equation for the angular position of the system, the equations of motion for an inverted pendulum on a moving cart is represented by the equations as seen.
Using the previous expressions which related cart displacement to pendulum position, a new expression relating servo displacement to pendulum position was generated. As a precursor to this expression, it should be noted that our main two assumptions were that the torque from the servo and the angular speed of the servo were both constant. From the assumption of constant torque from the servo, an expression which related servo torque to pendulum angular acceleration was generated. From the assumption of the servo moving with constant angular speed, an expression relating servo step size to time taken for that step size was generated. Next, in an effort to get an expression for the angular acceleration of the pendulum due to gravity, an expression for the torque on the pendulum due to gravity, and its moment of inertia were generated. Then, using the expression torque equals I alpha, an expression for the angular acceleration of the pendulum due to gravity was generated. All of these relations were plugged into the basic kinematic expression for angular displacement to yield the following equation. This final expression relates servo step size to gyro displacement.
By modeling the dynamics of the inverted pendulum cart system, we can establish the design constraints and limitations of the real-world model. The dynamic model of the system will allow us to understand how the model relates to the physical system and its resources. Some of the parameters mentioned earlier, such as pendulum arm length and pendulum mass, can be determined by measuring them beforehand because they are constant at all times. However, parameters such as angular rate and servo angle are variables, and in order to control the inverted pendulum system, these parameters must be known at all times while the system is active. Usually, control systems utilize the dynamic model of the system in order to control it. This is done by rearranging the equation that describes the system into a transfer function which relates an input of a system to its output. In basic feedback control, the transfer function of the system you want to control, which in our case is the pin-mounted inverted pendulum, is referred to as the plant. There's also the controller, the actuator, and the sensor. A feedback control system accepts a reference value input, which is a value that somehow relates to the desired output of the plant. It is compared to the actual value of the plant that is fed back using a sensor. The error between the actual value and the desired value is then sent to the controller, which generates an output signal to an actuator that in turn generates a plant input that has been corrected for error. Finally, the plant's output is checked by the sensor, and that information is then sent back once more to be compared to the desired reference value. A dynamic model can be a good way to approximate the behavior of the system, but since it is only good up to an approximation, additional adjustments need to be made to fine-tune the controller to account for the model's imperfect representation of the real-world